Hello. So in the channel, we're gonna start dealing a little bit more with complex numbers, and I will start doing something that's related to complex numbers, but it's not quite in the complex number realm, but it can be. So this is just a start, and I'm doing this horizontal. We're gonna have quite a few horizontal videos coming out actually. And I decided to do this horizontally because there's quite a few details here. So let's say we want to have a rotation operation in two dimensions for two vectors in which AB is an initial vector and A line B line or A prime B prime is the final vector. And we'll call V the initial vector and V prime the final vector. So that V is A x hat plus B y hat and V prime is A prime x hat plus B prime y hat. And we want to find an operation, r theta, that transforms V in V prime, so that if we are looking at this from the external point of view, we're gonna have an x and a y axis, a vector V. I didn't put it. This is the vector V. Let's put it. Oh, second. So we have a vector V that we want to rotate a theta amount to obtain V prime. They are composed in x respectively by A and A prime, and in y respectively by B and B prime. And you can see that we have an initial angle for V, which we call theta I, and our rotation angle is going to be theta. And the size of this vector V is the square root of a square plus b square, and we want our rotation to preserve size of vectors so that a prime square plus b prime square and the square root is going to be the square root of a square plus b square. With that in mind, and projecting each and every size that we're interested in, so that a is going to be the square root of a square plus b square cosine of theta I. B is going to be a square plus b square sine of theta I. A prime is going to be a square plus b square and the square root cosine of theta I plus theta. And b prime is going to be a square plus b square and the square root times sine of theta I plus theta. So that this transformation here can be represented by O1, O2, O3, O4 in a matrix that is 2 by 2 that multiplies a vector AB that's going to give us a vector A prime B prime, so that A prime is O1A plus O2B, as in we do this, obtaining this. So horizontal by vertical vector to give us the first element. And B prime is going to be O3A plus O4B, which is the second horizontal with the vertical to give us the second element of the vector. And if we expand the cosine with some of the identities that cosine have, we obtain this for A line, and we can do several things. One of the things is consider the versors, the versors that are involved, as in the vectors at the direction x with modulus 1 and at the direction y with modulus 1. So how would a transformation like this transform each vector? Well, x hat, which is the vector 1, 0, is going to give us an x hat line, which is going to be rotated by theta, by this theta, which means that x prime hat is going to be cosine sine in the vector notation, which means that r x hat is going to be r10, which is this result of x prime hat. This gives us the following, that the matrix of rotation times x hat is going to give us O1 and O3 cosine sine. This gives us the value of O1 and O3 incidentally. And doing the same for y gives us that y prime hat is going to be rotated by theta as well. We chose those vectors x prime hat and y prime hat to be orthogonal so that we can do this way. And y hat, pardon me, is going to be the vector 0, 1, which is going to be rotated into the vector y prime hat, which is minus sine theta cosine theta in the vector notation, so that a rotation of y hat is going to be a rotation on 0, 1, which is minus sine cosine, so that we can obtain the following, that the rotation matrix on y hat is going to be O2, O4, which is minus sine cosine, which incidentally gives us the values of O2 and O4, which means that this type of reasoning already gives us what is the rotation matrix. And we're going to talk about other things that the rotation matrix actually has, which is the rotation matrix is a linear transformation, as in it transforms a sum of vectors in the transformation of each component of the sum, so that it transforms the sum collectively in the same way that it transforms each element individually. And r times r in a vector that is stretched or compressed by a constant alpha x hat is going to be alpha times the rotation on x hat, so that r is called linear exactly because it doesn't do anything with a scalar in front of the vector, and it doesn't change how a sum of elements is actuated upon. That implies that r on vector AB is the same thing as r actuating on A0 plus r actuating on 0B. Let's make this more B, I suppose, which is A times r in 1, 0 and B times r on 0, 1, which is A cosine theta sine theta plus b minus sine theta cosine theta, which gives us that the transformation of a general vector AB in a general vector A prime B prime is going to be A cosine theta minus B sine theta for A, and this is now A prime, and A sine theta plus B cosine theta for B, which means this is B prime, so that we obtain, summarizing the following, r theta on V is going to be r on AB, which is the result we just obtained, which means that r theta, which we represented by this matrix, is going to give us O1A plus 1 to be O3a plus O4b in the vectorial notation, so that we obtain all of the O's, which means that the rotation matrix is gonna be cosine minus sine theta are the first two elements in the first line, and sine theta and cosine theta are the two second elements of the second line, as in A11 is cosine theta, A12 is minus sine theta, A22 is sine theta, and no, A21 is sine theta, and A22 is cosine theta. If A11, A12, A21, and A22 represent the matrix, as in this representation of O1, O2, O3, O4, O1 is cosine theta, O2 is minus sine theta, O3 is sine theta, and O4 is cosine theta. Why is this important at any rate? Because the rotation is a very ubiquitous type of operation, and because this will also be very useful for complex numbers, which we have things of this nature participating in the arithmetic operations or things that are analogous. And with that, that ends our small tour on finding the rotation matrix in 2 dimensions. It should be noticed that similar things can be done for more dimensions, and it can be decomposed in many of those, or you can use a general rotation in there. Both things can be done, and they're not a lot more complicated than this. And that's it. Bye for now.